So dear students, in the last class we were studying first law of thermodynamics. First law of thermodynamics is also called as the law of conservation of energy. So the law can be stated in many ways. So first way of stating first law of thermodynamics is energy neither be created nor be destroyed, but it can be transformed or changed from one form to another form. Another way of stating is when one form of energy disappears, an equivalent amount of another form of energy appears. And a third way of stating is energy of an isolated system is always constant. So you can learn whichever is easier for you. So then coming to the mathematical representation or mathematical way of expressing first law of thermodynamic. So first law can be mathematically represented as delta U is equal to Q plus W. So where delta U is equal to change in internal energy, Q is equal to the amount of heat absorbed by the system, and W equals work done on the system. So Q is delta U, change in internal energy, equals the amount of heat absorbed by the system, plus W is the work done on the system. If the work is done by the system, W equals negative. So W is positive, work done on the system. So W is negative, work is done by the system. Then first law comes to delta U is equal to Q minus W. So both are first law of thermodynamics. If work is done on the system, W is positive, work is done by the system, W is negative. So these are the mathematical representation of first law of thermodynamics. So what this says, the internal energy of the system changes due to heat and due to work. Suppose this is a system. So it has the internal energy U1 in the initial state. Let the internal energy is U1. When Q amount of heat is supplied into the system, its internal energy changes, that is U2. When the system changes from one state to another state, what happens? Internal energy changes. So internal energy of the changes due to heat, internal energy changes when the energy enters into the system or out of the system in the form of heat or work. So internal energy changes due to heat energy, internal energy changes due to work energy. So if work is done on the system, W is positive. If work is done by the system, W is negative. If heat is supplied into the system, Q is positive. If heat passes out of the system, Q is negative. So this is the mathematical representation of first law of thermodynamics. That means the change in internal energy is the sum of the amount of heat exchanged between the system and the surrounding, and the work done by or on the system. So now let us see note number 1. Change in internal energy. Change in internal energy delta U due to work. Change in internal energy delta U due to work. So from first law, of thermodynamics, delta U is equal to Q plus W. Q plus W, is it not? So suppose this is an adiabatic process. In an adiabatic process, what happens? The wall is insulated on all the sides. There will be no entry of heat. It is an insulated wall or adiabatic wall. So this is insulated wall, or it is also called as adiabatic wall. So here Q is equal to 0. There will be no entry of heat inside or outside the system. There will be no entry of heat inside or outside the system. Therefore Q is equal to 0. Therefore it is an adiabatic process. So this is a system. This is the system. So change in internal energy. So what happens if there is no entry of heat into the system or out of the system? The change in internal energy is due to the work, only due to work. So in an adiabatic process, Q is equal to 0. Since there is no exchange of heat between system and the surroundings, Q is equal to 0, and delta U is equal to what? Change in internal energy is due to work only. So if work is done on the system, W is positive. If work is done by the system, W is negative. So note, according to IUPAC by convention, if W equals positive, work is done on the system. Work is done on the system. So how work is done on the system? Suppose this is an insulated vessel. Suppose if there is water inside this vessel, this is the system. So by rotating the pedal, what happens? You can increase the temperature. You can increase the temperature from T1 to T2. So when the temperature increases from T1 to T2, its internal energy changes from U1 to U2. Then delta U is equal to U2 minus U1. Delta U is equal to change in internal energy is U2 minus U1. So internal energy, without allowing the heat to enter into the system or out of the system, if work is done on the system, what happens? The internal energy increases. So W becomes positive. Work is done on the system, that is internal energy increases. So if internal energy increases, U2 is the final internal energy, U1 is the initial internal energy, then delta U is equal to what? So U2 is greater than U1, delta U is equal to positive. delta U is equal to positive, therefore internal energy increases. If W is negative, if W equals negative, work is done by the system. Work is done by the system, that is internal energy decreases. Internal energy decreases. So, in an adiabatic process where there is no entry of heat into the system or out of the system, if work is done on the system, W is positive. If work is done by the system, W is negative. If work is done on the system, internal energy increases. If work is done by the system, what happens? The internal energy of the system decreases. So, change in internal energy due to work in an adiabatic process, delta U is equal to WAD. So, change in internal energy is equal to work done either by the system or on the system during adiabatic process. So, this is the first case. Second case, note number 2, change in internal energy, change in internal energy delta U due to heat at constant volume. So, this is the adiabatic walls. Now we will consider this system. It is a closed system. So, here Q is not equal to 0, that means heat can exchange between the system and the surroundings. So, this is the system. So, this is thermally conducting wall. Thermally conducting wall. So, and it is a closed system. So, internal energy changes of the system due to heat. What happens? Since the system is a closed system, and that means it is covered on all the sides, there will be no exchange of material from the system into the surroundings, and hence it is a closed system and it is a thermally conducting wall. So, from thermodynamics, first law, delta U, change in internal energy, is equal to Q plus W. Next, at constant volume, the work done, W is equal to P minus P into dV. We will going to study later on. P into delta V, delta, since change in volume delta V is equal to 0 at constant volume, W is equal to 0. So, W is equal to 0. Therefore, delta U, change in internal energy, is equal to Q at constant volume, QV. So, the change in internal energy is nothing but the amount of heat absorbed by the system or given out by the system. If heat is given out of the system, Q is negative. If heat is absorbed by the system, Q is positive. So change in internal energy due to heat at constant volume. So change in internal energy is equal to Q at constant volume, where Q is the amount of heat absorbed. So by convention, Q equals positive if heat is absorbed by the system. So if Q amount of heat is absorbed by the system, that heat is utilized only to increase its internal energy, because no work is done since the volume is kept constant. And Q equals negative if heat is given out by the system. If heat is given out of the system, it is negative. If heat is absorbed, enters into the system, Q is positive. So third case, change in internal energy delta U, change in internal energy delta U due to both work and heat, both work and heat. So the change in internal energy due to both work and heat is given by first law of thermodynamics, that is first law. Delta U is equal to Q plus W. So if internal energy changes due to both heat and work, then change in internal energy is given by delta U is equal to Q plus W. If internal energy changes due to work and heat, then if no energy enters into the system or out of the system, if no energy enters into the system or out of the system in the form of heat Q or work W, then Q equals 0, W equals 0, then delta U is equal to 0. So this system is an isolated system. So this is the meaning of the statement of the law. For an isolated system, the change in energy or the change in internal energy is 0. That means the internal energy of the system remains constant. Such a system is known as an isolated system. So we have studied first law of thermodynamics mathematically. Delta U is equal to Q plus W. So here Q is the amount of heat absorbed by the system and Q is the work done on the system. So delta U is equal to Q plus W. So if the change in internal energy only due to work, then delta U is equal to W. If change in internal energy only due to heat, then delta U is equal to Q. So when delta U becomes equal to W, change in internal energy is only due to work during a thermally insulated walls. Thermally insulated walls. So when change in internal energy becomes equal to Q, where it is a closed system and it is thermally conducting wall. So in the last case, change in internal energy due to work and due to heat is given by delta U is equal to Q plus W. If there is no entry of heat, there is no entry of energy either in the form of heat or in the form of work, then Q is equal to 0, W is equal to 0, then change in internal energy is equal to 0. Such a system is called an isolated system. That means the change in internal energy for an isolated system is 0, or for an isolated system internal energy is always constant. So this is about the notes regarding first law of thermodynamics. Now we will have an expression for work done during isothermal irreversible expansion, like that. Write down work done during isothermal irreversible expansion of an ideal gas. Work done during isothermal irreversible expansion of an ideal gas. Suppose here is a gas, here it is an ideal gas, and suppose it expands from volume V1. So this is volume V1. If it expands to volume V2, so this is V2. What is the work at constant pressure? So since it is an open system, what happens? The external pressure becomes equal to internal pressure. So during this expansion, what is the work done by the gas? Again at constant pressure P. At constant pressure P is given by, so write like this. If a gas expands, from volume V1 to volume V2 at constant pressure P, comma, then the work done by the gas, during expansion, W is equal to minus P V2 minus V1, or W is equal to minus P delta V. So where delta V equals change in volume that is V2 minus V1. V2 equals final volume, V1 equals initial volume, and P equals constant external pressure. So here pressure is constant. If pressure is constant, what happens? If heat is supplied into the system, the gas expands from volume V1 to V2. So the work done by the gas during this expansion equals minus P delta V divided by delta T. So this is the work done by the gas. Minus sign indicates that the work is done by the gas. Work is done by the gas. So similarly, we can write an expression for work done during isothermal. Isothermal means temperature remains constant. So Q is not equal to 0. Q is not equal to 0, where change in temperature. Isothermal means change in temperature, delta T is equal to 0. So during this condition, the work done by the gas during expansion W is equal, during isothermal irreversible expansion of a gas. Isothermal irreversible expansion of a gas, W is equal to minus P into delta V, where delta V is equal to change in volume of the gas from volume V1 to V2. Next, work done during isothermal reversible expansion. Reversible expansion of an ideal gas. Work done during isothermal reversible expansion of an ideal gas. So this is here, since it is a reversible process, maximum work done. Maximum work done. So in a reversible process, the process is very slow and you can get the maximum work done. So for this one of an ideal gas, we know that for an infinitesimal, we know that for a small work done, dW is equal to minus P dV. So here for a small work done, dW is equal to minus P dV, where P is constant pressure. Where P is constant pressure and dV equals small change in volume. So for very small change in volume, the small amount of work done, dW is equal to minus P into dV. So for n moles of an ideal gas, so this equation you have to assume for an ideal gas, n moles of an ideal gas, PV is equal to nRT. This is called ideal gas equation. Ideal gas equation. So we will learn in the next chapter. PV is equal to nRT. What is P is equal to? nRT divided by V. So substituting the value of P here, so this is equation 1, this is equation 2. So substituting equation 2 in equation 1. So dW is equal to minus, instead of P I can write nRT by V into dV, or dW is equal to minus nRT dV by V. Next, this is the small amount of work done. Then total work done is integral of dW is equal to minus nRT integral of dV divided by V. So from volume V1 to V2, this is W1 to W2, that is the total work done during isothermal reversible expansion. So it can be like this. So integral of dW is equal to W. This is called integration. So you will going to learn what is integration in your mathematics class. Integral of dW is equal to W minus nRT integral of dV by V is equal to log. Ln means log V2 by V1 to the base E. So to convert this base E to base 10, we have to multiply it with 2.303 minus 2.303 nRT log log to the base 10 V2 by V1. So this is the work done during reversible expansion of an ideal gas. So you have to remember two equations. W is equal to minus P delta V. It is the work done during isothermal irreversible expansion of a gas. So this is isothermal reversible expansion. So V2 by V1, where V1 equals initial volume, V1 equals initial volume and V2 equals final volume. R equals gas constant, that is equals 8.314 joule per Kelvin per mole. 8.314 joule per Kelvin per mole. This is called gas constant. T equals absolute temperature in Kelvin, and N equals number of moles of the gas. So this equation can also be written when pressure is given. So W equals minus 2.303 nRT log P1 by P2. So P1 by P2 because so P1 equals initial pressure, P2 equals final pressure. P2 equals final pressure when pressure is given, because V is inversely proportional to P according to Boyle's law. Since V is inversely proportional to P, we can write V2 by V1 or P1 by P2. So this is when pressure is given, given, this is when volume is given. So these two equations are very important, that is W equals minus P delta V and W equals minus 2.303 nRT log V2 by V1 or P1 by P2. So this is the work done during isothermal irreversible expansion of a gas. This is the work done during isothermal reversible expansion of a gas from V1 to V2 or P1 by P2. P1 by P2. So these two equations are very important. So next I will give you one or two notes. Note number 1, notes. First law of thermodynamics, that is delta U is equal to Q plus W, can be expressed for isothermal irreversible and isothermal reversible processes as follows. So first law can be modified. So first we will know, for isothermal irreversible process, for an isothermal irreversible process, for an isothermal process, for an isothermal means constant temperature. If temperature remains constant, internal energy change is also 0. For an isothermal process, delta U is equal to 0. So from first law of thermodynamics, delta U is equal to Q plus W. So here for an isothermal process, delta U is equal to 0 and W is equal to minus P delta V. W is equal to minus P delta V. So here 0 is equal to Q plus W, or Q is equal to minus W. So minus W means minus of minus P delta V. So that is equals, Q is equal to P delta V. So for an isothermal irreversible process, change in free energy is equal to 0. Therefore, the amount of heat supplied is utilized to do the work. All the heat supplied will be utilized to do the work. Therefore, Q is equal to P into delta V. So similarly this is first law. First law of thermodynamics modified like this: Q is equal to minus W for an isothermal irreversible process. Delta U is equal to 0. Therefore, Q is equal to minus W. But for an isothermal irreversible process, work done by the gas is equal to minus P dV. Therefore, Q is equal to P delta V. So, for an isothermal reversible process, so B, for an isothermal reversible process, how the first law is modified. First law, from first law of thermodynamics, delta U is equal to Q plus W. So for this process, for an isothermal, reversible process, delta U is equal to 0 and W is equal to minus 2.303 nRT log V2 by V1. Therefore, putting these two in this equation, Q is equal to minus W, that is equals minus of minus 2.303 nRT log V2 by V1, or Q is equal to 2.303 nRT log V2 by V1, or Q is equal to 2.303 nRT log P1 by P2. So this is how first law of thermodynamics modifies for an isothermal irreversible process. For an isothermal reversible process, first law is modified like this: Q is equal to minus W. Here also Q is equal to minus W, but W is equal to minus P delta V for an irreversible process, isothermal irreversible process. W is equal to minus P dV. So Q is equal to P delta V for an isothermal irreversible process. Change in free energy is equal to 0. Therefore, all the heat absorbed is utilized to do the work. Here also, for an isothermal reversible process, delta U is equal to 0. Therefore, Q is equal to minus W. So, work done during isothermal reversible process is equal to like this. So, Q is equal to like this. This is how first law of thermodynamics modifies. So, this is enough for today. We will continue tomorrow.